Alright, sorry I had to cut off on that last video. I ran out of time. So on these last two examples, this one is special because it's not actually equal to one of our special angles. So we have to really rack our brains and think, okay, what angle can we put in to get 0 out of the sine function? So to do this, I actually prefer, instead of thinking about the coordinate grid, to think about the sine wave. And I had you guys memorize that sine wave. And you know that it starts at the origin, works its way up to 1, and then comes back down to -1. Well, we can see very clearly that sine equals 0 here, here, and here. And this one's actually a repeat point, because if we continued the oscillation up, this would be a repeat point of the first one. So all we really need to worry about is the value here and the value here. That was the part that was always tricky for you guys, was figuring out, okay, what are the tick marks along this x-axis? Well, if we think about it like this, here's 0. The period of sine was always 2 pi. So halfway in between 0 and 2 pi is going to be pi. So now we know one of them is going to be x equals 0 degrees, and one is x equals pi. Or if we were doing it in degrees, let's do this one in radians since I already wrote pi, but it would be 180 degrees. Now remember, we have to look at all possible solutions, so that means we have to account for a full oscillation. So we're going to add, since this one we're doing in degree or in radians, we're going to actually add 2 pi in on each of these. And what that allows us to do is account for all the infinite oscillations of the sine curve. So we actually found all the possible solutions for this equation. And I didn't throw it into the earlier examples, but the way that this works is the n is in there to be a spot for us to plug in any whole number. So we can plug in 1 here, and we would get that another solution is x equals 0 plus 2 pi, which is 2 pi. And that's this repeat value I just mentioned. If we plug in a 1 here, that's going to give us x equals 3 pi, which is a little bit further along the sine curve. So you kind of get that idea of why these answers give all possible solutions. If all I wanted were the first two, then we could just have left the answer like this. But we want all. Alright, so our very last example, the only difference here is that we have to actually do step 1. Step 1 said isolate the trig function on one side of the equation. So far we've actually had all of the trig functions isolated. In the future lessons that won't always happen, but here's an example of where it doesn't happen. So what do we want to isolate? Well, we're going to treat cosine theta like our variable. We're going to try to get both cosines to the same side together and then isolate it. So first I need to move this 7 cosine theta over with this -2 cosine theta. So I'm going to subtract and just treat it just like an equation. And then these two are going to cancel. So now we have 9 equals -9 cosine theta. Now we've almost got the trig function by itself, but it has a coefficient, a -9. So we need to get rid of that -9 by dividing. So now we have -1 equals cosine theta. That's the equation that we're going to solve now. So we just had to, that was just step 1. So over here I'm going to write example of step 1. Now we have to actually go through determining what x can be for this equation to be true, or in this case theta. What can theta be for this equation to be true? Again, -1 isn't one of our special angle ratios. Normally we have like square root of 2 over 2 or 1/2 or something. But this is one of those quadrantal angle answers. So what I'm going to do is actually draw my cosine curves. In the last example we did sine. This one I'm going to draw my cosine curve. And it starts at 1 and dips down to -1. And remember, cosine's period is also 2 pi. So halfway in between is at pi. And it crosses the x-axis at pi over 2 and 3 pi over 2. So our question is, when does cosine equal -1? Well, this is one of those rare instances where it only equals -1 at one spot. Okay, it only equals it right here at pi. So we're going to say that theta equals pi, and we have to account for every oscillation, so we're going to put plus 2 pi in. And that's it. So today I wanted to give you guys a lot of examples so we could have a lot to go off of tomorrow whenever we talk about this in class.